Cool. All right. So the main topic for this week is sorting data. And if you haven't gotten a chance to look at your assignment for this week, you are going to be sorting the tasks that come from Airtable. And you're going to do it initially by passing some extra data to your URL when you make the request for tasks in Airtable. And then after that, you'll be writing the sorting yourself in JavaScript rather than letting Airtable do it for you. I don't think it's explicitly clear in the instructions whether you're supposed to remove the sorting through Airtable once you finish and then do it with JavaScript instead, but that would be my guess. So probably you'll write some code to have Airtable sort for you, and then you'll take that out and then write the JavaScript to do it yourself. But just for the sake of talking about some interesting stuff, here's some questions that I want to answer. Number one, why are we particularly interested in sorting data? And also, like, what is this sorting algorithm? Why are there so many? And what should you be aware of? So if we have really any amount of data that's going into a table, or not even going into a table, maybe you're just designing an API that someone's going to be requesting data from. A lot of use cases will demand that you be able to sort data by one or more properties of that piece of data. So if I have like a user object and I have multiple users in a list, I might decide that I want to sort the users by first name to try and figure out, who shares the same first name, or sort by last name so I can put together an ordering of how I should handle individuals. Or maybe there's other data associated with the user, like an age. I can sort by the age field, which shows me the oldest people or the youngest people first, so on and so forth. There's an extremely common need in any kind of programming to be able to sort just an arbitrary list of data. And there's a lot of ways of sorting, but not all of them are great for whatever use case you have. So I could have a piece of data that's just a list and it's just a bunch of numbers. And in this case, with just a couple of numbers, it's not super important how we go about sorting two pieces of data. This list is very small. It's a clear ordering. Numbers are very easy to compare. But most of the time when you're sorting data, you're going to have a lot of pieces of data, and sorting all of these things can get expensive very quickly as your number of data points grows. The other thing we need to be aware of is, what if I have a list that's not just numbers? Maybe I have a list of user objects where everything has a first name, a last name, an age, so on and so forth. If I have multiple of these objects, what do I have to do in order to sort by age? How do I actually compare these things? And then when I can compare two different objects, how do I turn that into, let's sort my list based on this property? So I can compare two objects here, but then what do I do in order to say, oh, this object should come first, this object should come second? So one of the links that I want to give you guys today, if you have not already found your way onto the site Geeks for Geeks, this is a pretty good website for just general computer science inquiries, or if you have a question about specific algorithms that you come across, they'll usually have a write-up for that. This site, I think, has a bunch of ads on it if you don't have an ad blocker, which I do. And sometimes it'll pull up a banner that forces you to sign in, but you don't have to do that. So we have the concept of a sorting algorithm, which allows us to say, given a list of things and given some function where I have two pieces of data, I need to determine which one comes first. So that function could be any implementation you want. In the case of a number, maybe the function just says, is my first number less than my second number? In which case that one comes first. Otherwise, if my second number is bigger than my first number, well, then the second number comes first. That's a sorting function. And then a sorting algorithm says, given that function that can compare any two arbitrary pieces of data, well, take my data and actually sort the entire list using that function in order to figure out how to swap things around. And there's a bunch of different terminology in here that is not super important right now. Just ways that we measure the efficiency or the behaviors of any particular sorting function. I think the most important thing that we should have a discussion about here is complexity, time and space complexity. I don't know, probably have not had any experience with big O notation. But it is something that's really important to understand once you get into the computer science field. Big O notation is a way that we can measure two different algorithms to say which one is literally faster or which one literally takes up more space given an arbitrary input. So I need to be able to describe an algorithm no matter how big of an input I give it. I could give it a list of 3 items. I could give it a list of 47 million items. I need some way to concretely measure how long the algorithm takes and how much extra space on my computer in memory it takes up to execute. And so we do this in relation to the input, which let's sort of just briefly discuss this before we go any further, because I think it is useful. Here's what we're gonna do. Yeah, we'll discuss what that means in a second, but generally, yes, that's what we're aiming for. Okay, so I have an algorithm which just is like a function that does something, and it takes in an input and it does some computation here, and then we get an output. That's it. That's all we mean by an algorithm. It doesn't have to be anything more complicated than this, although, you know, some algorithms get really complicated depending on the kind of problem they're trying to solve. An algorithm, we can use this to sort a list. So I take in my list here, which is some array of some kind. Maybe it's an integer array. Let's say this is an array of numbers. And let's do this. Let's call this are there has duplicates. And we're going to write a function that tries to determine if there's 2 or more numbers in the list that are the same integer. So what I might want to do is I'm going to say, if I have an input of 1, 2, 3, 4, 3, I want to take each number and compare it against every other number in my list and see if they're equal. And if I get through the whole list and don't find another 1, then I know the 1 is not a duplicate. And so then I check this 2. Is there a 2 anywhere else in the list? No. Is there a 3 anywhere else in the list? Yes, and I return it at that point. So let's write this really quick. So, all right. So I goes through the entire list, J goes through the entire list, and then we compare if they're the same. But we don't want to compare if I and J are the same number. I don't want to compare 1 against 1, and so on and so forth. So if I is equal to J, then we're going to continue, which just skips this loop and immediately runs this loop again. And then if list of I is equal to, I need a triple equal, list of J, and we're going to return true because we found a duplicate. We return false if we don't find any duplicates. All right, so this is an algorithm. It finds duplicates in a list. Oh, shit. Thank you. All right, there we go. Now you can see it. All right, well, this is what I was writing. This is a function has duplicates, and I have a list of numbers. Let's say this is our list, and we loop through the entire list, and then we have another pointer which goes through the list. So this starts at 1, and then this starts at 1 and looks through the whole list. Then I goes to 2, and this looks through the whole list. And then we compare the two numbers together and return true if we find a duplicate. So we have this algorithm. We have no idea if this is good or not. We need some way to objectively say, well, is this a good algorithm? And the way we do this is with big O notation. And big O can measure either a runtime or a space complexity. And we say that the runtime of this function is O of n squared. What does this mean? Well, we always prefix it with O, and then we put the runtime on the inside. And we want to describe this in some way that is indifferent of what the actual size of my input is. So this algorithm takes in a list, and so we want to say this algorithm runs, given the list length, which we're going to say is n numbers, we want to describe how many operations this function is going to perform in relation to that length n. Well, this goes from 0 up until but not including the length of the list, which counts n variables. So I is going to start at 0, 1, 2, 3, 4, which is a total of 5 operations. And then inside of that, each time we do 5 more because we start at 0, we go through the length of the list. And so this goes and checks 5 different numbers. And then we change this, and this checks 5 more. So essentially, if we're saying everything on the inside of our loop is one constant operation, we are doing one comparison. This is our one operation. Well, we're doing it 5 times, and then we're doing those 5 times 5 times. So this is times 5. This is times 5. In the case of n equals 5. And so this would be saying we're going to do this 25 times. Well, we don't want to measure in terms of a literal number because list could be an arbitrary length. So if this is n and we replace 5 with n, this loop runs n times. Each time this loop runs n times. And in total, we run this one operation n times n times. Or n times n operations. And so that's how we get our n squared down here. We're saying this algorithm performs n squared operations if the list is of length n, because our first loop goes n times, and then each time the first loop runs, we run n more operations. And this can be really complicated. If I took this loop out, well, now this is just O of n. We loop n times, we do something. And I could also have a bunch of other things down here. Operation 1, operation 2, operation 3, blah, blah, blah. We generally don't include any constants. We only care about anything that is in relation to n. Because if this n gets really big and has a million different items in the list, well, we don't care if it happens a million than 3 times. We care that it happens a million times. And similarly, if this is really small, we don't really care if it happens 4 times or 7 times. We only care about the n because the n is the part that gets really big when the list gets really big. There's a lot of complexity here. I and j in this case are just 2 different variables that I'm using in my code. I and j are not important to measuring the complexity of this algorithm. Ignore I and j. I could call this anything I want. The only variable we care about when we're measuring our complexity is the input, and the input is n elements. Any more confusions before we go any further here? This is like as far as I really want to go. Like we're not going to get really complicated or do some practice with this right now. If you're interested, I think it is worth looking up in the future. I'll post the links in the Notion page, and they're also in the agenda. But we're not going to take this any further today. This is a tangent so that we can understand sorting algorithms rather. Okay. If there are any questions, speak up. All right. So we have a way of measuring how long this takes. We can also use this notation for how much extra memory our function uses. So if we think about all the variables we create and all the data that we create, the only things we're creating are 2 integers. We're creating a number that goes in I, and we increment it using our operations down here. We create another j. So this is our runtime complexity of n squared. That's how many operations we perform. Our space complexity is also measured in O of n, in big O notation. But in this case, n is still the length of this list, but how many like literal pieces of data in memory are we creating? In this case, I'm creating one little piece of data for this variable I and one little piece of data j, and that's it. That's all I'm creating. Everything else is just an operation. And so I'm basically creating 2 things. But again, we don't care about like constant values. We don't care if this is 1 thing we're creating or 3. The space complexity we would say is O of 1, which means it is constant. Every time I run this function, it will create a constant number of things in memory and never any more or never any less. If I were trying to get the duplicates for this function, and I created an extra array somewhere in here, and let's say every time we found a new item, we're going to add it to this list. By the end of this function, this list here will now have every single item in list added to it. So how much extra space are we creating? Well, we're creating a duplicate of everything in list. We're creating it twice. So if there's n elements in here, the number of things we've created is n. Whereas here, it's just like a constant number 2, because we're only creating 2 things. Here, if we pushed every element into this list, well, we're creating n new data points, because this list is now also going to look exactly the same. And so this space complexity would be O of n instead of O and 1. We're creating n new items, given that n is the length of our list. And this can also be represented in lots of different ways, depending on what kind of data structures you're using to solve your problem. This could be n squared, this could be n cubed. Generally, n squared is really bad, and you would like to do anything in your power to have a complexity smaller than this. But sometimes you can't get always what you want. Any bigger than n squared is probably going to be problematic unless you know that you're going to have a small set of data, in which case maybe it's fine. Maybe you don't care if you have 4 items in a list, whether your runtime is O of n or O of n squared or O of n cubed or anything like that. It doesn't really matter. All right, so keeping this in mind, we have these 2 ways of measuring how long a function takes to execute and how much extra space on my computer it takes up in order to perform its function. That space gets freed as soon as this function ends, because we no longer have use for this other list. And so that will get cleared up by our computer automatically. But while the algorithm is running, we do care how much extra space it takes. So back to sorting. We have lots of different ways of sorting data that have different runtime and space complexities. There's lots of different sorting algorithms. And you can go and look at all these different sorting algorithms yourself if you want to. This is a very long list. You do not need to know all of these. You don't need to know any of them, really. You might get asked some questions about sorting algorithms, like if you're doing a technical interview. It's fair game. There are questions about them, but generally we don't, as programmers, care about this because I'm not writing my own sorting algorithm. For the most part, any language you work in will just do that for you behind the scenes. And you can just call a function that says sort my list of data. You should be aware that sorting is hard to do quickly and will take a lot of time if you have a really big input. And so maybe if you have a big input, you want to try and find any way you can to not perform a sort because it's going to take too long and your site's going to be slow. But if you do need to sort data, you should be aware that it does take some time, and under the hood, it's running with a general runtime complexity of O of n times log of n. So this is a logarithm. This is how most of our sorting algorithms work. There are some very dumb sorting algorithms that run in O of n squared, which is not ideal. The most notable one would be a selection sort. And a selection sort is like exactly what you think about when you're looking at an array and trying to sort it by hand. You look through the whole thing and say, 1 is my first number. Actually, let's change this. So I would look through this whole list and I would say, 1 is my smallest number. I'm going to move it up to the front. We're going to replace it in the back with 5. So we're just going to swap those out. Oops, 2 is my next, 3 is my next, and then 5 is my next. So we're going to swap that out with 7. Great. That's a selection sort. We didn't talk about any of the implementation details because it's not important for you right now. But that's a very basic sorting algorithm, and that runs in O of n squared complexity, which is not ideal. Most sorting algorithms will run in n times log of n, which is a lot better for really big inputs. Log of n is going to be like a fraction of the actual size of n. So just like a quick recap on logarithms, this is log base 2 usually, I think. Uh, and so a logarithm would say, well, if I have 8 elements in my list, let's start at the bottom. If I have 2 elements in my list, it's going to take 1 operation. And if I have 4 elements in my list, then it's going to take 2 operations. If I have 8 elements in my list, then it's going to take 3 operations. And 16, 32, 64, so on and so forth. If I'm getting this wrong, I apologize. It's been a while since I thought about logarithms. But it's like an inverse of an exponential power of 2. And so you can imagine this number is getting big really fast, but this number is not. So if I have a really big input of like 1 million different elements, well, 2 to the 1 millionth power is going to be really, really big. So our 2 to the 1 millionth power is going to be a huge number. I don't even know how big. Let's look it up. Big number calculator. Can someone like send a message in the chat about whether you can hear me right now? Okay. I don't know what the deal is with my browser. I was just concerned if it was like a internet thing or not. Oh, we're back. All right. Cool. This is 2 to the 1000th power. So if I have 1000 elements in my list and I tried to sort them in an n squared complexity, oh no, no, no. I'm sorry. I got this all wrong. That would be 2 to the power of n complexity if we were doing this, which is not the same as n squared. N squared would mean, let's do this. So if my value, if my list size is 1, 5, 10, 100, 1000, 1 million, then this corresponds to an n squared of 1, 25, 100, 10,000, 1 million. And then this is 1 trillion, which is a lot of operations. And then log base 2 of n. I think this, I need a calculator for this. This is what I thought. So this is 0. and then n of 5. So 2.3219. 10. 3.32. What is 100? 6.64. 9.97. 19.93. So if I had an algorithm that ran on this list even in O of n time versus O of n, or versus O of log n, we still would take log of n way more than we would take O of 1. Would I rather do 1 million operations or like 20? These are not like perfect round numbers in general. Like you can't do 2.32 of an operation. So we would say this would be like 2 operations or 3 operations, depending on how you round. But especially for sorting n squared for this many elements, like a million things, you can't sort a million different data points with an n squared runtime because this will take minutes to complete, whereas this will probably take a couple seconds. And this would be n times log of n, which would be 1 times 0 and 1, 5 times whatever, and 10 times 100 times 1,000 times and 1,000,000 times. This would be 0. This would be roughly 10. This would be roughly this would be 33.2, and this would be 664. And 970, 1993, 0000. All right, so this is running 19 million operations instead of 1 trillion. And this is running about 10,000 instead of 1 million. So again, it's not perfect. We're not just running 19 operations. That would be great. But this is still a very good reduction and allows us to actually sort data reasonably. So in general, we want to pick something that has a better runtime complexity, but maybe our particular problem that we're trying to solve with sorting, we are fine if it takes longer. Maybe we just like have a computer that runs in the background and can go as long as it needs to. But we have a very small amount of memory on our computer and we can't afford to use too much space. Well, in that case, maybe we want to pick an algorithm that has a slightly longer runtime complexity, but a smaller space complexity. Just depends on what you're trying to accomplish. Generally, I think runtime is more important, but there will be use cases where you have to consider space as well. All right, tangent over. So again, we said selection sort, very basic. A lot of these other ones are a lot faster. But in general, your language is not going to make you care. You don't have to know how to actually write all of these. It might not hurt to be familiar so that you could talk about it in an interview. You might get questions about different kinds of sorting algorithms. But in your day-to-day, you probably will not write any sorting algorithms. Rather, you'll just write the comparison function that says, given my 2 pieces of data, how do I decide which one needs to come first, which one needs to come second? So let's look at how we would write a sort in JavaScript. We're going to get rid of all of this. And we're going to create another function here called get oldest user. And this is going to get a list of users. And what is a user? Actually, we're not gonna. Yeah, we'll do it. We'll write a JavaScript class rather than making this TypeScript. If this were TypeScript, I would just make a type for it. But we'll make a class. A constructor, so every user is going to have a first name, a last name, and an age. We'll say this dot first name is equal to first name. This dot last name is equal to last name. This dot age is equal to age. So what is this? This is a class. I can create user objects from this class. This class is just a blueprint to say what should a user be able to do? What data does it have when I create an object? And it's going to have a first name that attaches itself to the object. A constructor is what we use to create a new object. It takes in 3 inputs and it creates a new object where this object's first name is equal to the first name input, and this object's last name is equal to the last name input, and this object's age is equal to the age input. So I can create a user like this and give it Eli Smith and 23. And similarly, I could create another user for my little brother. Who is, I think, 16. Don't quote me on that. Cool. And so now I have 2 users, and this is how we would create objects. So now I could get my user dot first name or dot last name or dot age, and then use that at any point. So let's say I have a list of a bunch of different users. And then we'll just create some random users. That'll be 7. This guy'll be 55. Cool. So we have a bunch of different users with a bunch of different properties, and we're going to put them all into a list. User 1, user 2, user 3, user 4, user 5. And then we're going to declare this function, and we're going to say get oldest user. Some users. We're going to log it. And just for the sake of this demonstrating sorting rather, we're going to sort this list, and then we're going to just take the first element, which we expect after we sort to be the oldest user, and we're going to return that. There's other ways we could do this without sorting. We don't need to sort to do this. We could just look at every single item and keep track of the oldest age that we've seen. And then we'd only have to go through the array once. That would be more efficient, but we're going to sort just for the sake of it. So let's do it. So in JavaScript, arrays have a lot of different methods that you've probably used, but it also has a sort method. I hover over this. This is the definition of our sort method. Just gonna close some stuff so I can see it. So an array of any type, this never is sometimes substituted in for, it doesn't know what type of array it is. It could be anything. And this sort method takes one optional parameter. This question means it's optional. It's a function that compares any 2 arbitrary elements in my list. So if I have a list of just numbers, I can call dot sort and it'll just work. I don't have to give it a function. It knows how to compare numbers. It'll put the smallest number at the front. But maybe I want to reverse it and I want to sort by the biggest number instead. Well, then I would have to declare my function to compare two different numbers. And the way these functions work is you need to return either a negative number, 0, or a positive number. And I don't know if it's going to show us. Yeah. This comparison function should return a negative number if the first argument is smaller, 0 if they're equal, or positive otherwise, meaning the second number is bigger. That's how every sorting function you ever write in your life will work. If you want A to come first in your sorted list, you should return negative. And if you want B to come first, then you should return positive. If they're exactly the same and it doesn't matter, then you return 0. So for a number, if I want to sort this in reverse, then I would need to make sure that n2, the bigger number between n1 and n2, needs to come first and the smaller number needs to come second. So I'm going to say if n1 is bigger than n2, well, I want my bigger number to come first, so I'm going to return -1. Generally, we always return -1, 0, or +1. If you have some sort of mathematical operation that results in a negative or a positive, you can do that. But if it's not like a mathematical operation like subtracting or addition, people generally stick to the convention of -1 or 1. So again, the sorting algorithm, this sort said if the first argument is less than the second argument, meaning it needs to come first, then we should return a negative. Well, if I'm sorting in reverse, -1 should come first because it's bigger, or 1 should come first because it's bigger, so we return -1. Else, if n2 is greater than n1, then I'm going to return 1 and say n2 should come first, and otherwise they are the same thing according to us. We can test that here. So this is sorted in increasing order, and at the end, this should be in decreasing order. And we'll go ahead and run this. Oop. Got to put new. Cool. And so it prints us out the numbers after we sorted them, and now they're in the right order. So this is how you write a sorting function. You determine which one should come first. If n2 should come, if n1 should come first, you return a negative. If n2 should come first, you return a positive. Otherwise, you return 0. And we can do this with more complicated data types too. Let's do it with our data, our user data here. So our oldest user should be at the front of the list, and then we'll just return whatever's at the front of the list when it's done. So we're going to say sorted users is equal to users.sort. And we're going to give it our comparison function. So this function takes in user1 and user2. And if user1 dot age is greater than user2 dot age, well, then I'm going to return -1 because user1 should come first. should be earlier, else if user2.age is greater than user1.age, return 0 or 1 rather. Otherwise, we don't care. They're the same for our purposes, and so we're going to return 0 to say they're equal. So we're going to return whatever's at the front of our sorted users list, which we said the older people should be at the front of the list and the younger people should be at the end. So of these people, I would expect Billy Bob Joe to be my oldest user. Let's test it out. Whoa, Billy Bob Joe. And I can reverse this if I want to. Let's write a function, get youngest user. And we're just going to flip this around. If U1 is younger, then we'll return that. Otherwise, if U2 is younger, then we'll return that. Otherwise, we return 0. And we'll print this. Cool. 7 is the youngest age, Robert Woods. Sweet. So this is generally what you're going to have to do for your assignment. You have a bunch of different tasks, which are going to be in Airtable, and Airtable will give them back to you in an arbitrary order. You don't know which task is going to come first, second, third, so on and so forth. And every time you get the data from Airtable, or every time you submit a new task, it's arbitrary where in the list it's going to fit. And so you'll be writing basically what we did down here. You'll be using the sort method and then providing a comparison function that compares two to-do items together to figure out which one should come first and which one should come second. And then this sort function, this just exists in JavaScript by default. You don't need to know how it's implemented. This is just the definition in TypeScript of how it works. We don't see any implementation details, but behind the scenes, this function is using one of our sorting algorithms that we discussed over here. And then in order to compare each element against each other in that algorithm, it just calls the function to say which one should come first. So it might be using a merge sort or a quick sort in order to sort the whole list. But when comparing individual elements to figure out how it should rearrange, it's going to use that comparison function you get. You don't have to care about the underlying implementation. The creators of your web browsers where the JavaScript is running, or Node where you're running your JavaScript, they've implemented JavaScript's sort function using one or more of these algorithms. And which one it's actually using is not super important. If you're running it in a browser, each browser implements JavaScript a little bit differently. And so they might use different sorting algorithms. And then Node also is like a different implementation of JavaScript. And so that probably also has a different implementation. Does it matter? No, not for you guys. In case you're interested in reading up on it. All right, that's all I got. Any questions about anything we talked about? Could be questions about Big O in relation or not in relation to searching and sorting. All right, if anything comes up, I'm always available. Feel free to reach out. I do think, given the attendance this week and given that next week is a review week and we're kind of heading towards the end of the class and the next cohort is starting, which I'm also volunteering to help with, I think probably I'm not going to run a session next week and beyond. I think this will probably be the last one. If you have any questions about assignments or you're working on your final project and you need help, I think there might be other group mentors that are still running their sessions, and there are always one-on-one mentors, so feel free to bring questions directly to them. But with that said, I will probably not run any future group sessions, but I will still be available for reviewing assignments or answering any questions as needed. Thanks for sticking with me for 16 weeks. I had a great time. It's really helpful to me to be able to run these sessions because I get to like really dig into topics in a way that I don't normally do if I'm just writing code for myself. And it's really been an honor to be able to meet all of you guys. And I wish you guys all the best of luck with your final projects, with your practicum if you go into the practicum, with apprenticeship if you go into apprenticeship, or if you go in a totally different direction. I hope you guys have a great future ahead of you. And I'll always be available. If you haven't connected with me on LinkedIn or anything like that, please feel free to do so. You can find me on LinkedIn pretty easily. All right. With that, I will close out. Have a good weekend, everyone. I will see you hopefully in the future. Same to you guys.